Hello and a very warm welcome to today's tutorial. This is our second session in the tutorial series about distance protection. My name is Nina Hühn and I am promoter for differential protection. Today I have the honor to guide you through this webinar. In the first session you learned something about the method and implementation. Gustav explained some examples to get a better understanding and showed special applications of distance protection. The topics for today are zone grading, residual compensation factors, and parallel line compensation. These 3 points are explained with an example of an overhead line. Further topics are power swing blocking, outer reclosure with secondary arc detection, and measured voltage failure detection. The expert presenting the topics today, as already mentioned, is my dear colleague, Mr. Gustav Steinberg. Gustav has been working at Siemens for almost 30 years now, and he's a technical expert in all areas of line protection. I'm sure we can all learn something from him today. Of course, one more thing, you will have the chance to ask questions. You can type your questions in the question field in the upper right corner or in the chat during the whole webinar, and I will be your voice and read the questions to our expert. We will have 2 short breaks. Q&A sessions are planned before the break and at the end of the session. All the questions that we won't answer today will be answered after the webinar in a written format. So please don't hold back and ask everything you want to know about distance protection. Yeah, and now I'm happy to hand over to Gustav.
Thank you very much, Nina. And welcome from my side. And I hope you have brought some attention because we are going to carry on similar to the last session and look at distance protection from a more practical point of view. Now, we cannot, technical problem, small technical problem. The presentation today, as Nina said, is going to be a more practical application in that we're going to look at an example, and I will focus also on the parallel line compensation a little bit because during the first session there were a number of questions regarding parallel line compensation. The other subjects we'll get to in time. So without further ado, let's get right into the overhead line example. Now, when you are going to apply the distance protection to any situation, you have to collect the data. And obviously, as you can see at the bottom here, impedance data, this is for this overhead line, is very important as the distance protection, impedance protection will be working based on an impedance loop measurement, as we already discussed. The impedance, as you see here, come in different formats, but you will typically find here, as you can see, R1, X1, or Z1, depending on how it is given, it doesn't really matter, is your positive sequence impedance. That is also going to be very closely related to the reach setting. For the ground faults, we'll look at that in more detail later on. You need the zero sequence impedance of the line as well. This can be given as an absolute total line impedance, or as in this case, you're given as a per kilometer impedance. And then you obviously need to know the length of the line. And from basically on this data here, we can really calculate most of the critical settings for the distance relay. Also shown is the tower geometry. From the tower geometry, as we know from the first session, the arc resistance is going to be calculated from the length of the arc, which we also base on the insulator length or the separation of the conductors as seen here. And finally, what could and is very critical also is how is your system grounded? As you see on the complete left over there, is it a solidly, effectively grounded system? Is it with resonant grounding? And the example we're doing today is going to be with an effectively solidly grounded system. For the Peterson or resonant coil grounded systems, obviously one needs to consider differently because ground or single phase faults are not real short circuits, are treated differently on those cases. But that is a different subject. Today we are looking at effectively grounded systems. Another aspect then relating to that is obviously your instrument transformer, your CT-VT connection, as you see here. We need the data from the CT-VTs for the application, the ratio, and as mentioned in the first session, the conversion primary secondary is important. You need to check, and you can in Dixie, as you see on the complete bottom left-hand corner there, in the orange block. This time the setting there is applied as a secondary impedance. You can also apply your settings as primary. So very, very careful that you don't get that mixed up, because there is a difference. You have to convert the primary to secondary based on the CT-VT ratio. This is the equation you can use where you can take the primary impedance here and multiply with the CT-VT ratio as shown, and then the result would be the secondary impedance. That's important, okay? The other aspect we come to now is a little bit more general CPROTEC 5 application or methods of implementing relays. Not really going to this in detail. This is if one is new to CPROTEC 5, maybe one should do a Dixie type course, which will explain all the steps necessary. But just quickly speaking, you can see here, and this is if you apply a new device in your Dixie, you enter at the top either a short or long product code. What you see at the right at the top there is a long product code. You don't have to type that off by hand. Normally you'd imply that copy paste, or you would enter a short product code. That is the hardware description of the device, okay? It's basically what you have purchased. And if we do this, we basically make an offline version of the relay, or basically a Dixie-based version of the relay. And the next step, that is just a piece of hardware at the top. So when we implement it in Dixie, we have to typically choose at the bottom a template. And the template you can take from the standard library. And you can see I chose in this case for not a breaker and a half, but a single breaker, solidly grounded system. And I choose the firmware version, and then you can apply that. If you do this on a regular basis, then you would obviously have your pre-configured starting configuration, which you want to use. And you can use a user-defined template as well, which is very helpful to simplify the engineering process. But that's not our subject today. We are talking about distance protection. So let's move on to the next thing and try and find where is the distance protection located now in the device. On the left, you see that is the project tree that's also shown in Dixie. And in that structure, you'll find there is the function group. You see the function group line there. And inside that function group line, they would find the distance protection about 5th or 6th from the top in the function group line. You can see it there, 21 RM distance protection. That is implemented there. If you want to apply a classic or another one, you can delete it there and from the library add that to that, or if there are, but also from a template point of view, delete, because you see there's a lot of functions there. You may not need all of them. Delete the ones you don't want and configure your device as required. That is that point. The other thing that we did see, we have to always see the CT-VT connection that is shown in the other templates here, is another key aspect for the relay. If you're going to apply that, you have to obviously make sure that the CT and VT is connected to the function. That is done in the Dixie configuration under the measurement point routing. And you can see here, physically in the middle, that would be the current measuring point. So I have defined here 2 current measuring points. It's interesting, the one, a 3-phase current measuring point, that is going to be the one connected to the protected line. And as mentioned at the beginning, we want to look at parallel line compensation. So if we're going to apply the parallel line compensation, we also have to measure the ground fault or residual current from the parallel line. And that's what the second measuring point, you see, it's a single phase measuring point current is applied here for at the moment, just as IX. You don't know yet that it's parallel line. It is just a measuring point at this point. It is nothing more than that, right? And also important, if you have to really work with a relay on site, you don't need to refer to any manuals or pamphlets to find the terminal numbers. In Dixie, you can see the terminal number of the device at the top here. There is the actual physical terminal, and the IA phase current is connected there, and so on. And the parallel line residual current, as we'll see later on, is connected to this terminal here. At the bottom, the voltage in a similar manner. There also a 3-phase measurement for the line and a single-phase measurement probably for a sync check, maybe a bus bar voltage for sync check. Not a subject we'll cover today, but I just showed it there for you to see for completeness. All right, that is, I think, Dixie configuration as you would do it. This is a graphic representation, maybe easier to explain, to re-emphasize what we just looked at in how you do it in Dixie, just a picture of that. At the bottom, you see this diagram, and in this diagram, you can imagine that the outer block, the gray block here, is a physical device, and a physical device would have terminals to the outside. Here, you can see here, binary input-outputs would be binary inputs and outputs, and so for the trip signal to the breaker, maybe the close signal to the breaker, feedbacks for breaker auxiliary status, and so on. And on the complete left, you see also terminals to the outside. That would be the current measuring point and the voltage measuring point. And those we have just assigned, remember? And to those terminals, remember what we said there? And those are then internally considered as a logical measuring point, which is then routed to the function group. Remember, our distance protection was inside the function group line. And you see that middle blue block there. In the middle there's the 21, our distance protection, and it derives its measuring point from this function group line. And as I say, the logical measuring point current, completely on the left there, is used in both function groups, the function group circuit breaker and function group line. The trip command that we root out, and also the feedback, the status, because there are functions in the line that need to know the status of the circuit breaker, that you don't derive that directly from the outside. Here you derive this via a function group circuit breaker, because all the logical devices like auto reclosure we'll see later on, those are not implemented inside a line, those are implemented in the circuit breaker where they belong, like a sync check function, auto reclose, breaker failure, and so on, are done inside a function group circuit breaker. And the trip command of the line goes to this logical circuit breaker, and the circuit breaker then processes that onto the outside. This is the structure of cProtect 5. But I think that's enough of that cProtect 5 structure. Let's get back to the distance protection. And one of the key settings or things that one has to remember in distance protection is the so-called residual compensation factors. It's a name. Maybe you know them better as KR or KX here. Also, sometimes cProtect 4, you might know them as RE, RL. Well, I showed it here, RER1, XE, XL, or XE, X1, your residual compensation factors, as we know that. Why can I replace R1 and RL? And you see it in the diagram here. You see that the impedance, as it is shown in the three phases there, is the ZL, which is RL plus JXL. That is your positive sequence impedance. For it to be a positive sequence impedance, that is our assumption, is that those three-phase impedances are exactly the same and balanced. That's the definition of a positive sequence impedance, and that then can be substituted directly. So we can replace that RL, XL, in this case exactly, by the positive sequence R1 plus JX1, the definition. So what am I trying to show in this diagram? In this diagram here, I connect my three phases with a short circuit at the end of the line, so to speak, and I inject at the beginning 3 voltages, and the 3 voltages I inject are those 3 blue arrows. They are exactly in phase and identical. So if in that case, what voltage is that? That is the zero sequence voltage by definition. But the zero sequence voltage means that it is exactly the same in all 3 phases, magnitude and angle. That is a zero sequence voltage. What you could do in this case, you could make a short circuit here because the voltage there is identical, and replace that injected voltage with a single U0 zero sequence. All right, what else can we derive from this diagram and what this diagram is used for? Because with this diagram or this connection, you can measure the zero sequence impedance of the line. And this is then done in a reverse technician because you have a definition. As you see in the block there on the left, definition, the definition of the zero sequence impedance is U0 divided by I0. So that is our definition. So with this circuit then and our test conditions injecting there, we then can make this voltage loop equation in our classics way and go around one of these paths, just one, you don't have to go around all 3 of them. You can choose any one, but they're all the same. The injected voltage is U0, and then you go through an impedance here, which is your positive sequence impedance, ZL. Remember ZL I said was your positive sequence impedance. And then you come to the bottom point here, but here, be careful. there are 3 I nodes coming down here. Each one will have exactly the same current because it's balanced, as we said at the beginning. So you'll have exactly I node plus I node plus I node. So you'll have 3 I node coming down here and flowing from right to left back to the source side. So if you make a loop equation over there, it will be I naught times ZL is the voltage drop here, and 3 I naught times ZE would be the voltage drop here, and that is going to be equal to U naught. Be very careful with your signs over here, with the plus sign. Remember here, if we were using IE instead of 3 I naught here, it would be a minus sign, because remember, IE is equal to minus 3 I naught. It has to do with the direction, because the arrow, as you see over there, is defined in the current flow for IE, positive always in the direction of the protected object, the line, but the I naught is flowing in the opposite direction from right to left. So that's why IE equals minus 3 I naught. But for the loop equation, this is the correct way to do that. Taking the definition and substituting this for the U naught in the definition, you then get this bottom equation here. And then if you divide the I naught into the top, you get the simple equation at the bottom there. Very interesting. If you look at that, Z naught equals Z1 plus 3ZE. What can we derive from that? We can see from that that Z naught on an overhead line can never be smaller than Z1. On cables, the ZE can be a bit strange, depending on single phase or 3-phase cables and so on. But if we look at overhead lines, the ZE will always be similar to, well, larger than the Z1 even. So the Z naught cannot be smaller than Z1. That's very interesting. All right. Rewriting that equation, following the orange arrows, we then come to this equation here. We can then derive ZE, and this is the important thing that I wanted to say. In the diagram at the top, remember we said this was Z1, but this is not Z naught. This is ZE down here in this diagram. Be careful to relate to basically get from Z naught to ZE, you have to use this equation. Z naught minus Z1. All right, and then from there on in, we can calculate this RE, R1. Remember, R1 is the same as RL. As such, the Kx over here. And we derive these 2 equations from that. Why do we need to do this? Okay, so it seems like we're calculating 2 factors here, the Kr and Kx effectively as they are known in CPROTEC 5. Why did we do this? And we did this because, and here we are showing from the manual, the classic ground loop or ground fault calculation formulas, the method in which the X is measured during a ground fault, or the R is measured during ground fault, the way the impedance is measured by the distance protection for ground faults. And you can see in those formulas, the Kr and Kx factors appear a number of times, not just once, they appear a number of times in those equations. Why do you use this rather intricate method? Because on the left-hand side of these 2 equations, what you see there, the measured impedance is the positive sequence impedance. So we can apply the same reach setting. Well, later on, we'll apply reach settings. And we then no longer discuss, is it for a ground fault, is it for a face-to-face fault? It doesn't matter, because both the face-to-face faults and the face-to-ground faults will measure an impedance which is basically the same. It is the positive sequence impedance, or as shown here, the loop impedance. And the setting, we can therefore apply the settings, the reach settings, based on positive sequence impedance. Okay, having done that explanation, now we come back to our example. Remember the example, we had the data given here for the line, the 60-kilometer line with these impedances. And now we can substitute, we derived the equations on the previous diagram. We can substitute the impedances here into the equation. You can see I substitute the R naught, which is a 0.165 over here, and the R1, 0.028 over here into the equations we derived, and I can calculate the Kr and Kx, and then I would set that in the relay. And the similar for the Kx, that is that setting. So that we have dealt with, that's the first one. Interestingly, at the same time on that diagram, the line angle was set and so on. Those are standard settings you need to apply. The line length was set here, that's for the fault location, is interesting. And also the impedance per kilometer in primary was set here for the fault location. Right. Right now, I'm going to jump into the parallel line discussion because it fits in there a little bit with the KR, KX settings and so on. And then, as I say, after the break, we'll carry on with the zone grading. So for the parallel lines, there is a modified loop equation because the influence of the parallel line, as shown over here, is going to add an additional voltage drop when you do your loop equation. Okay, and this coupling that we have shown here really only exists in the zero sequence. Why in the zero sequence? Because if you consider the three conductors under normal operation, they will have a current flowing out and back. And if it's a phase-to-phase or three-phase fault, then the sum of the currents of each line will add up to zero because the current will flow out on phase A, back on phase B, and it'll be, if you capsule that, it'll be effectively zero. But if you take a ground fault, the current is flowing out on phase A and coming back via ground. And the ground, you cannot just bundle and sum up like that. The ground will couple into the other system. That's why in the zero sequence or in the ground path, we have a significant coupling due to this parallel line factor. The diagram we see here is typically used for the explanation. It's the parallel feeder end to end. Both sides, the bus bar on the left and right, the two feeders are coupled. And what you would then have typically, if you have a fault towards the right-hand side over here, you'll see something similar to this, that the ground fault on both lines will flow towards the fault location. So obviously on the faulted line, it'll flow to the fault location and then back. And on the parallel line, it'll flow towards the fault location via a remote bus bar and then back to the fault. So for the line that's seeing the fault close to the remote end, where you could have the risk of overreaching, because remember, if the fault is close here, then we are not going to get overreach this side. But if the fault is close to this bus bar, the mutual coupling could make an overreach, and we need to be careful. So for the remote faults, we typically have this condition. Now, what under that condition, the IE and the IE parallel line have a similar direction. Okay, so if we look at the voltage loop equation over here, they will affect the voltage in the same manner. And you can see both factors are minus. The three terms in this bracket over here, the first one is IA, and then you see minus ZEZL, that is basically K naught or the KR, KX combined as one complex factor. I didn't want to write it out in KR, KX, then the equation would become unmanageable and not easy to recognize. So this is a simplified way of showing that, and also used with a complex calculation, even using an RMT method, you can use it. If you do a complex calculation here, this technique is still the same as the other one. But you see the first two terms would be without the mutual coupling. That is our classic line. That means we have no parallel line over here. Adding the parallel line adds this additional term here, and you can see it is also a minus IEP times this factor here. So if the IE parallel line and the IE have the same sign in the equation, they will increment the voltage. Okay, and remember what we did during the first session. If we have incremented voltage, the distance protection will underreach, it will not overreach. So the parallel line influence, as shown over here, will have no overreach. Okay, it will basically, so you have no risk of non-selective tripping under this kind of condition. So normally the parallel line is not going to be a critical thing in terms of overreach. You'll tend to see the fault a little bit further away. You'll have an underreach a little bit. However, there can be constellations where maybe the parallel feeder is open to that point, or sorry, the protector feeder is open on this side, and the fault current will come from here, down here, and round the loop back here. Not so serious, but if the breaker is open here, you cannot overreach. Okay, so also conditions like that are not critical. But the one shown at the bottom here is a very interesting one. If the parallel line is taken out of service and grounded at both sides, if you take a line out of service for maintenance work, etc., you would typically, for safety reasons, apply a ground at both ends. Then it would look like this. The protected line would be in service, and the parallel line would be out of service and grounded at both sides. If we now get the fault close to the remote end, or even the fault on the bus bar here, which is the critical one, then you'll see something interesting will happen. you get a current flowing, zero sequence current, or IE, flowing out on the line, and on the parallel line it will couple and flow back in the opposite direction. It is coupling, so the mutual coupling will make a circulating current flow here, and that current is flowing opposite to that one. And that would create an overreach. So during the parallel line open and grounded condition, one must be careful. One may have to apply some settings to reduce the reach, or, as we will show now, we have the option to apply a compensation. So this is the parallel line background. Interesting, if you look at this equation, we'll come back to that in a little while. It's a loop voltage. You can use that at any time to calculate the voltage drop on the protected line during a fault with a parallel line coupling. For the compensation, as we said earlier on, we have to measure the residual current of the parallel line. So you can see in this diagram now we have two relays and two feeders, line 1, line 2. These are two parallel lines. And what you can see is for the one line, you have this protected relay. It's measuring the currents from its CTs over here. And on that I4, as we did at the beginning, remember that was our IX routed as the fourth current input. That is connected to the parallel line. It will measure here the residual current, the return current from the parallel line, the IE of the parallel line as such. At the top, you can see now that's actually that previous equation, the voltage loop equation, extended now into the KR, KX method. So you can see it gets a bit longer, but it's essentially the same thing. You can split the real and imaginary components as you've shown there in the two tops. That's the same voltage loop equation there, but not written with Z's, but with R and JX as such. From that, you can now see that that R naught divided by 3 times RL, that is going to be our mutual coupling or KMX factors. Similar to the KR and the KX factors, you calculate if you have a parallel line a so-called KMX, that is for the zero sequence mutual coupling consideration. And then we can rewrite the equation at the top and substitute the ratio ZX naught 3ZL. We can substitute with the KMX, KMR. And the important thing, obviously, is if we then rewrite this, we can calculate the impedance. So the impedance calculation equation we saw early on are then modified to consider the parallel line compensation. Okay, that is the connection we did. And this is now just showing you how it was implemented in Dixie. Remember, I had my parallel line current was the I4 current here. That was this one. I assigned that to that point over here. And that you have to, that was our mirroring point routing we did early on. And now interesting here, in the function group connection, remember we had the blue blocks, which were the function groups. You were connecting your function group line to the CT here. This is this CT over here. Remember, this is the CT over here, the top CT, the three-phase CT connected here. And you also then say parallel line current, also connected to the function group line, is that single-phase current from the parallel line. And rename it. You can see on the complete left, I renamed that current measuring point I, one phase, IE, line 2. So you know it's the line 2 IE current, for example. You can rename it as you desire. That's important. So if you've done that, if you have a parallel line current, then you have the option in the settings you see at the bottom here. You set that KMR and KMX, which we have calculated at the top. Your data of the line obviously is then expanded. You need to have additional to your positive sequence and zero sequence impedances. You also need your mutual coupling impedance values here so that you can calculate those data at the end. And this I did in an example. This is a different example. The previous example was a 400 kV, doesn't matter. For the parallel line, I used here 110 kV with slightly different data, but it doesn't matter. It's the same thing we do in application on 110 kV line. Okay, and having done all these settings, you then can apply that. And the question you could have now, is this all correct, what I've done here? Okay, so what you can do, obviously, is trying to use an Omicron to test that. Maybe if you don't have an Omicron, there are other options. You can use the so-called digital twin, and that's what I did. Applied the settings to a digital twin, and then calculated some currents to be injected here to see if everything is working. So here you can see this is a setting. Also under the distance protection, you have to say apply parallel line compensation. Yes, so then you actively say you want to use the distance protection with mutual compensation. Okay, what I then did, I took Excel. You can see there's the results of my Excel calculation. I take this equation. It's not so difficult. I mean, if you're interested, I can maybe make available the Excel calculation sheet in the download area. It's not very complicated. I used this equation and I created some fault locations. You see I took maybe 60%. I took two faults at 60%. I made M 0.6 times the line impedance. And then I defined a current. I think it was 3,600 amps for the one case over here. And then the IE would be automatic. So in this situation, I keep things simple. You can see there's no fault resistance or anything in there. And then I assume that my IE is going to be equal minus IA. Just make a normal. Otherwise, you have to make a more complicated injection. But so I just inject an IA current. And the IE will be minus IA. So it's a simple loop in the protected line. And I inject in parallel and IE parallel. And you can see that's the results you see over there. Test case 1 is the top line. I'm injecting the current 6 amps over here on the protected feeder. And that would mean it's minus 6 amps IE on this top feeder, and the parallel line current was 0. So that would the parallel line current just out of service, not working. That was my first test case, just to make sure that even without the compensation, everything is working. So it would just be the calculation as you see there, IA K naught times IE. And then for the second test case, I now inject the current IE in the parallel line, 4 amps at 180 degrees. What case is that? That is this case over here, where the IE and the IEP are in the same direction for the second test case. Remember, because I'm injecting 5 amps, as you can see, into IA at 0 degrees, that means the IE on the protected line is 5 amps at 180 degrees, or minus 5 amps coming back the other way. So the 4 amps here, that means we have in this second test case 5 amps here and 4 amps over here. And the 4 amps and ground currents are parallel. Normal application, remote fault. And again, it was at 0.6, just to compare the two results. So both the first two faults are both at 60%. And then finally, I did a case for the bottom here. I moved the fault to 85%. In that case here, and I injected 6 amps on the top feeder and 5 amps in the bottom, but the 5 amps in the opposite direction. And it's interesting, if you look at the voltage magnitudes, although the third test here has 6 amps and 5 amps in the parallel line, you can see the voltage on the complete left is only 45 volts secondary for the third test, although it's larger current. Normally larger currents would give us larger voltages. If you compare it to the first test was also with 6 amps on the protected feeder, and it was 46 volts. So the 5 amps on the parallel feeder actually reduced the voltage. That's what we expect. And that's the risk that this final case can give you an overreach. You see, we have the same current in the third test as in the first test on a protected feeder, but a smaller voltage. So we would, and the fault is further away. Remember, for the first test, the fault was at 60%. Gave you 46 watt, and for bottom test, the fault is at 85%, and you still get a smaller voltage. That is the significance of the parallel line in feed. All right, so I tested all those with the digital twin. All right, and you can see the screenshot. That is not a photograph I took of a real relay. That's a screenshot from digital twin. And on the left, you can see that was similar to an Omicron. What's it called? The quick CMC. You just inject 3 voltages and the fault current. You can see that's my first test case with the voltage. Be very sure to put the right angle in, that 77 degrees. And then the 6 amps on the IA phase current. And at the bottom, you see 21 kilometer. 21 kilometer is that 0.6. Remember, the line was, I think, 30 kilometer, 35 kilometer line, I think. I can't remember exactly, something like that. But that works out. The 21 kilometers is exactly what we expected. So for the normal case with no current in the parallel line feeder, so IEP is 0 during the first test, we get the expected result here, 21 kilometers. So those settings are correct. Now we do the second test. We now again at 60%, but we apply a parallel line current right at the bottom. You can see 4 amps, and the 4 amps are in the same direction as the IE on the protected line. So 5 amps on the protected feeder, and 5 amps coming back IE on the protected feeder, and 4 amps on the parallel feeder. And again, you can see the fault locator. Remember, this is the fault locator. It's not really distance protection, but the fault location and the distance protection are both using the compensation at this point. So at least the fault location indicates that we have done everything correctly for that test. And then we do the third test. The third test is at 85%. That should be 29.75 kilometer. You can see it came out correctly. And for the third test, you can see the IE on the parallel line is in the opposite direction to the IE on the faulted line. Small voltage, and yet the impedance is furthest away from all tests so far, because it is obviously at 85%. It works correctly. Then finally, what I did just to check something is, over here, we did just a relook at this case over here. This fault should be seen in zone 2 and not in zone 1. And if one looks here carefully, you can see here it was a zone 2 operate for that second case. And the fault location is at 29.8 kilometer where we expected. This is the fault log for that test case, just to show there's a correct zone 2 operation, not zone 1. So distance protection did not overreach. The fault was seen correct at 85%, did not come into the 80% zone 1 setting. So that proves that also the distance protection is working correctly here. Only a zone 2 operate, no zone 1. And the fault locator there is also working correctly. What I then did as a final check quickly is to disable that. You can go into the settings, and in the settings you can switch off. Remember, we saw the setting early on where I said apply mutual compensation, yes or no, for the distance protection. Didn't change it for the fault location. So you can see I retested that test 3, the one at 85%. And you can see the result. The fault locator is still showing the 29.8 kilometer. But because I disabled the parallel line compensation for the distance protection, you can see it was a zone 1 operate. The impedance moved into the zone 1. So you can see the importance, if you're going to apply that, to do it correctly. But if you calculate your parameters suitably, you will get a good result as that. And that's a nice way of checking that. And the digital twin, I can recommend that if one wants to simulate something like that or check it, it is a nice way to confirm that your settings are done correctly. All right. Are there any questions at this point?
Yes, there are already some questions. Many questions about auto closure. So
Okay.
People are very curious about this part, I guess. But of course, we will start with the questions about parallel line compensation, matching to the first part. And I start with the question from GB. What if we have SIP5 and another manufacturer relay on a parallel line?
Yeah, if the relay on the parallel line does not really affect you, because remember, when we are doing the parallel line compensation, we are just deriving the current from the parallel line. That's all we need. We don't really have to have any other interaction with the relay on the parallel line. All we need to do is make the connection. You have to open the start point, and then the residual current flowing back to the start point of the CT, you have to loop that into our relay, and that is the IE of the parallel line. This is just the importance.
Thank you. So another question about parallel line compensation from WSH. Gustav, thank you very much for the great presentation. I have a concern with parallel line compensation. We sometimes have a parallel line that don't terminate at common stations. Therefore, the measurement of the zero sequence current of the coupled line can be a challenge. What are suggestions for this scenario?
This is unfortunately the most common condition for the parallel line, that it is not, as I showed an example, end-to-end. In some short lines in distribution, you have the end-to-end as we had the example, and you can apply it. But if you have only a partial parallel line and you don't have access to that, then you have to consider it in the settings. As I showed you, you then have to calculate, and there are methods. There's also an application note that we can dig out. It was done for CPRODEC 4, but the principle still applies, in which you can then modify. You can calculate modified KR, KX settings. Typically, normally, especially the KX setting, you modify that with an equation to then avoid the overreach. So you basically make the ground current have a shorter reach. It's not so nice, but that's the price you have to pay for the parallel line coupling.
Okay. So one last question about parallel line compensation, I would say. Would this compensation method also work or is applicable in a case with example 3 or 4 parallel lines?
That's, I think, what I said at the beginning. It's not really possible. If you're going to have more than one parallel line, remember the coupling is defined for the coupling between one feeder and another. The Z, that K, there's a Z0M, the mutual coupling impedance, is the coupling between one line and another. And if you've got a coupling between one line and another, and another, then you have to expand this and you end up with a matrix. So you basically, instead of having just the 4 impedances in the loop, classically you would have to expand that for each parallel line with an additional loop calculation. And that is not done, and is basically not done, as mentioned by the previous question, that typically you don't have that end-to-end. If you have really an application with 4 lines going end-to-end in parallel, then you have to just reduce the reach, and there's no way of doing the compensation for that.
Okay, I understand. Yeah, I would say these are enough questions for the first part. Unfortunately, we have a tough schedule. Maybe just some general hints. Of course, you will get access to the recording and to the slides. Simply follow the registration link. And yeah, if you are interested in the Excel calculation Gustav mentioned, you can contact him or contact us directly. And of course, as already mentioned, we don't have the time to answer all the questions in this session today, but of course, we will do this in a written format afterwards. So now we have time for a short break to give your eyes and ears some rest and get a cup of coffee. So we will continue 10 before 10. So around about 7 minutes, and just simply stay in the meeting. We will also stay here, and yeah, see you later.
Okay, see you later.
So welcome back from the break. I hope the time was enough to get a cup of coffee or to get some fresh air, open the window. And now with a fresh mind, we want to start in the second part. And the topics for the second part is that Gustav wants to continue with the overhead line example. And he wants to talk about zone grading and power swing blocking. So stage is yours.
Thank you, Nina. And yes, welcome back. Now we carry on to the distance protection classic conditions, the setting and the zone grading. Back to our original example, the 400 kV with the 60 kilometer line and those impedances. We are going to now calculate the R and X setting for the zone 1 and later on also show the zone 2 conditions. So the first thing we're going to do is do the resistance. And for the resistance, we are going to need the arc length as shown, the 5 meter for the single phase. That's over one isolator string to the tower, the 5 meter length. And for the separation of the face-to-face conductors is 12 meters there. With that, we can calculate the arc resistance, okay? And for the ground faults, and I'm going to focus on the ground fault. Remember, for the face-to-face fault, we only have an arc resistance. There's obviously no tower footing resistance. It's just that 15 meter separation face-to-face is relevant, not the tower footing resistance. But for the face-to-ground fault, it consists of two factors, the arc and also the tower footing resistance. And the sum of those two is the effective RF that we need to consider for our setting. So to take the examples here, we take those 5 meters and you substitute that in this equation. This is what we also showed in the first session a couple of weeks ago, the arc resistance, so I don't want to spend too much time on that. We use a 2,500 volt per meter arc voltage. That's fairly conservative. Typically voltages will be smaller than that. Okay, that's on the higher end, so we don't really need any additional safety margin. That is a very, very conservative, in other words, a large estimation of the arc resistance. One does not need more complicated things like Warrington equation. There is not really any gain because at the end of the day, it's a large uncertainty. The 1.5 is a factor because the arc will typically not be in a straight path. So we don't just simply use the 5 meters. We extend the 5 meters by a factor 1.5 to make allowance for the curvature of the arc as such. And then you need to obviously know a fault current. In this case, this is the fault current as measured by the relay, not the sum of the fault currents from both ends as such as we need for the tower footing. Here, because remember the arc voltage is a voltage, and we simply going to measure that voltage, and that voltage and impedance, as for us, our relay is just going to be that voltage divided by the current that we are measuring. So relevant here, that fault current is the local in-feed fault current to the fault. For the tower footing resistance, again, as not done before, there's a number of, in parallel, the current will go flash over to the tower, and then it will separate along the ground wire and come down on parallel tower footing resistance. So we don't look at one, it's basically a combination of those in parallel. And we use, example, this graph here will give you some typical values for a single or a dual earth wire. And this our tower, it's a single earth wire. So we on the blue curvature. And then based on what each tower footing resistance is, you can estimate a resistance of about 2 or 2.5 ohms for the tower footing resistance. All right, and we calculate that in our case for the tower footing resistance at the bottom. You can see the arc resistance, first, the 6.25 ohms there. And we do that with a 3 kiloamp in this example for the local current. And for the tower footing resistance, as I said, you have to consider the remote in-feed as well, because it's an ohm. It's now a resistance like Ohm's law, and the sum of the currents must be considered. So we have to summate those the 2 kiloamps from locally and the 1 kiloamp remote. There'll be 3 kiloamps flowing through the resistance, and we will only measure with 2. So we have to basically apply this remote in-feed consideration. So the 2 ohms tower footing resistance that we extracted from that graph over there is multiplied by this factor and actually are used in the equation as a 2.5. It's interesting, if the remote current were also 2 kiloamps, then we would have multiplied by 2, then we'd have here 4 already. So the remote in-feed is very, very significant in terms of the RTF. It's not something I'm covering here in this presentation, but it's something specific. If you have weak in-feed concentrations, you may have to, in terms of the resistance, consider successive sequential tripping considerations, because you cannot obviously apply here a ratio of 10 kiloamps from the remote side, 1 kiloamp here, then you multiply this by 10, you end up with 20 ohm arc resistance here, and very big settings will come to symmetry later on. One has to be a bit conservative. All right. Then to set it, we would summate those two to get the fault resistance. And then again, it's important to check if we are using a classic distance protection as we are doing here for the ground faults in the classic, the RF is divided by this factor 1 plus KR. Why is that done? I'm not going to go through it in detail now. I think we did that in the previous presentation. It is because the equation that we're using to calculate the ground resistance, as shown early on with those factors, extracts the positive sequence impedance. Remember, we have here the loop current will be the ZL out and the ZE return, but measured and applied in this curve here is only the positive sequence impedance. So this resistance here is not part of the positive sequence, it's not part of the E, it's somewhere in between. And the way the method of measurement deals with it, it separates it into one portion into the positive sequence and one portion into the ZE. And that separation factor is this 1 plus KR. So what actually appears in the measurement with the classic is not RF, but RF divided by 1 plus KR. So that is what we must use in the setting when we are going to set the resistance reach for the classic. And you can see in the green over here, that's where I calculated that. The 1.2 is a 20% safety factor. So 1.2 gives you a security that you would definitely see the resistance. And then you multiply that, the sum of these two resistances as we calculated them on the previous slides, and divide it by that 1 plus KR. Oops, sorry. I read KR in the equation, but over here it should be divided by 1 plus KR. Actually, that's actually a mistake I just found. Ooh, so you see, even there, you can do mistakes and you just see me. It should have been divided by 1 plus KR, not just by KR. Okay, so even smaller setting. That would be then applied there. And for the phase-to-phase, you would have to then take the 12-meter arc resistance, because only arc resistance is considered for phase-to-phase, the 2,500 volt per meter, 1.5 safety factor. And for the phase-to-phase, we consider 3 kiloamp as a local in-feed for a phase-to-phase fault. That's slightly bigger current than on the phase-to-ground fault. And that gives us 15 ohms setting for the phase-to-phase. Well, I think that should also be divided by 2, but never mind. Okay, so the setting for the zone 1 reach now, this is the X setting. The X setting is calculated basically at 80%. Our typical zone 1 safety margin, as we discussed also in the previous, that you need to consider on the complete measuring chain, CT, the instrument transformers, the relay, and also important, your line parameters can vary. Also seasonal variations, wet days and dry days can have different line impedances, especially in the ground loops. Hot days and cold days, it's not huge differences, but there is always going to be some tolerance. Your measurement is never that perfect. And we use 20% typically. That's why I only set to 0.8, not to 0.9 or 0.99, to make sure that the zone 1 never overreaches. That was our discussion during the first training session when we said the zone 1 is an underreaching zone and may under no circumstances trip for an external fault. And that 20% safety margin is what we use for that purpose. You can see here the remote bus bar, and then we set 20% short of that, and that makes sure that we will never see an external fault in the zone 1. That is our grading here, and calculate it like that quite simply. But as I think mentioned in the first session, we now cannot just move on. We have to now, before we finalize this, check the symmetry. And the symmetry condition has to do with the measuring tolerance, as I mentioned that, because we have got tolerances and the 20% safety margin must consider that and must obviously be larger than our tolerance. So I just made an example and say that The 20% safety margin we apply was used to take into consideration a real tolerance of 10%. That means, but if you look at the 10% tolerance on the impedance, you see the circle radius here is showing the tolerance. So if the fault is here, due to 10% tolerance, it can be anywhere inside that yellow circle. And as you get closer to the other side, the impedance gets shorter and therefore the circle radius gets smaller. But what is the problem? If this encroaches here, that means surely that with a 10% measuring error, you could see the fault inside the zone 1. Although this is a 20% tolerance, remember that is only calculated based on the X. So this is 20% tolerance on X, but if you take the Z is twice as long. That's why the 10% tolerance comes into the reach. And that is obviously unacceptable. You don't want the zone 1 to reach in. It's an example. Okay, the real tolerance problems are not as much as 10%. They are way smaller than that, maybe in the order of 5%, and one can live with that, but this is just a graphic form showing that why one needs to consider this carefully. So let's check what was our result. So in our case, we have set here 7.5 ohms was the requirement on the R setting, and for the X setting, we had 16.8 ohms. So we are at a ratio smaller than 0.5. So we are really on the safe side. You can see way on the left here, very safe. And if we look at the table that we use as an orientation from the manual, you'll see that for a line here, remember we have a 60 kilometer line here. And for that, we can orientate here that we should have a ratio somewhere between 1 and 2. This is not a rule. It is just an orientation guide. But if we are at 0.5, then we're going to say, all right, that is maybe a little bit small. We will just increase the R reach until we have a ratio about 1 to 1. That would be what I would recommend. So increase the R setting there to about the same as the X. All right. That's the end of the zone 1. Let's now look at the zone 2. The zone 2 setting has got a different requirement. Remember, the zone 2 is our overreaching zone, and the definition in the name says overreaching. It may not fail to see an internal fault. So there we apply a 20% safety margin again, but this time overreaching. So you can see it in the factor there as 1.2 times the line impedance. So we have, as you see at the bottom there, a 20% safety margin, but overreaching. So we have to set it to 120%. That is the requirement. That's what we will set. You can maybe on short lines say maybe set it 150%. That's fair, but it must be at least 120% under typical conditions to give you that minimum safety margin of 20%. The other boundary you see now, and there is another boundary for the zone 2. The zone 2, in terms of our selectivity concept, may not pass or encroach beyond this zone 1. So let's have a look at this little graph over here. Our protected feeder is the one on the left with the R line and plus JX line over there. And then we have the remote bus bar over there. That's up to where we must reach, and the zone 2 must reach beyond that. And then on the next bus, on that bus bar, we have other feeders. And the one we need to worry about is the shortest feeder coming out of the bus bar over here on the right-hand side. That shortest feeder is going to, in our concept, have also distance protection, and that will have a zone 1 setting. So on that shortest feeder, and this would be this one over here, you can see it's shorter than the one on the top. That's our shortest feeder. It has a zone 1, this blue zone 1 over here. This blue zone 1 is a setting of the distance protection on this feeder here, the remote bus bar side, outgoing feeders. Our zone 2 may not pass this point. What will happen? What will happen if our zone 2 picks up for a fault over here? Then we will run our zone 2 time, and what will happen? This zone 1 will not trip. So what will happen? The zone 2 on this feeder and our zone 2 will probably trip simultaneously. And non-selectivity, a loss of selectivity or a bad grading condition. That's why we again apply our magic 20% safety margin, but this time back from here. You can see that over here. So we must make sure that our zone 2 does not encroach into this boundary here. In other words, conflict with the zone 1 here. We grade always a zone 1 with a zone 2. So our zone 2 is graded with this zone 1, and it must not overreach this zone 1. So we have to go back here. And remember, this 20% here is not calculated with this feeder impedance, but with the loop impedance as it would be seen by our zone 1. Okay, so we grade. That's where you can see this 20% here is a significant portion of this line can be that 20%. So if that boundary is over here, then you can see, all right, we have here a little separation. I'll say we have set this value here, and that value is smaller than that value. We have a separation here, so we are okay. That's why it says okay. If this point here had been beyond that, we would not be okay. I did not show a graph like that. Then what you have to do, you'd have to increase your zone 2 time grading, 1 time grading step. Okay, which is a good point because time grading step, that is our next subject. All right, so just to conclude, we are going to apply the fault resistance settings based on the arc resistance over here and the X setting based on the tolerances over there. But before we conclude, we must remember that the R fault we are using here for the setting is going to be different in the RMD, because the RMD for the phase to ground and only for the phase to ground loops. For the phase to ground loops, the RMD technique, remember that is not the classic, the alternative to the classic distance protection. The RMD protection is using a different way to calculate the ground fault resistance, only that one setting. And that one you have to then apply directly. And for RMD, you set it directly. You don't divide it by KR. You set this RF directly. So the 10.5 ohms here calculated is basically 120% of this RF arc over here directly. That's a small difference. That's where the RMD setting is different to the classic. And also from a symmetry point of view for the phase to ground setting, therefore on the RMD, you can approximately double the symmetry. So for a classic, you would have basically the 1 to 2. For RMD, you can use a 2 to 4. You can double that tolerance. But that's another subject. All right, time grading. What I wanted to get to. Time grading is something that when someone just accepts that, okay, my time grading step is 250 milliseconds or 300 milliseconds or something like that. In this example, we're calculating a 250 millisecond time grading step. But where does that come from? Why do we use that? And obviously, we know we use that as shown here in this diagram again. For example, for a zone 2, that the zone 2 will not trip before the zone 1 on the remote bus bar has cleared that fault. You can see the fault there, the red fault arrow there on the single line diagram. External fault, our zone 2 at the bottom in that 21 relay is picking up on that fault, but its time delay will run, and typically a zone 2 time delay will be 250 milliseconds. And before that time expires, the top breaker will have opened and removed the fault, which brings us to this diagram where we can maybe explain that a little bit. So at the top, you see the red arrow. That's time 0, the fault inception. There's a pickup delay. All the relays must measure. They will not instantaneously pick up when the fault appears. There's a small measuring delay. The measuring delay is very commonly 20 milliseconds or shorter. I just showed it as 20 milliseconds as an orientation over there. All relays will have something in that order, maybe a little bit faster. 10 milliseconds, the zone 1 trip can be even faster than that, possibly, depending on the context you are using and so on. But it doesn't matter. That's just an orientation. For our time grading, we will use this 20 milliseconds as a general pickup time. The zone 1 at the top will then, after 20 milliseconds with a 0 millisecond time delay, immediately give a trip. So after that 20 millisecond pickup, what is now happening? You see the breaker time here. That is the breaker opening time of that circuit breaker CP1 at the top there. It's while it's opening. And that will take 2, maybe even nowadays, 1.5 cycle, 2 cycle breakers. In that order, what you can see, I took here 1.5 cycle breaker, 30 milliseconds, a really fast breaker. It could be slower, 2.5, 50 milliseconds, doesn't matter. When that breaker is then open, obviously the fault is removed and our zone 2 will drop off. But again, you have a drop-off delay. For the drop-off delay, I took 25 milliseconds, something in that order. So at that point, you can see here, we are safe. Our zone 2 has dropped off and we will not trip. The bottom relay will not have a non-selective trip. Coming on to that is a huge safety margin. So you can see here the safety margin in this case is about 175 milliseconds. And then you say, but why? I could have made the zone 2 timer much shorter. Yes, you could, in theory, if that is the only consideration you have. Typically, it is not done, okay? And probably one of the main reasons why one typically has longer time grading, okay, before I get on to the next slide to show that, is remember the zone 2 has another purpose, which we sometimes forget, because it's just a little additional information. The zone 2 has the function of remote backup. So what does it mean, remote backup? Remote backup and the distance protection generally does a very, very effective remote backup functionality. Remote backup is that if this fault that we are seeing here fails to be cleared, the relay at the top, that's zone 1, that relay is does not pick up. Maybe it's VTS failure, or maybe its contacts are breaking, or maybe the trip coils are broken, or maybe the DC has failed, or something goes wrong in a station there, and that protection fails to clear that fault. That's where the zone 2 then comes in. The zone 2 will then clear it here. When the time delay expired, it will trip as a so-called remote backup functionality. Okay, that is something one must remember. And that is why one also needs that's not the primary purpose of zone 2. It is a secondary purpose of a zone 2 to do that. In this remote backup functionality, it can be that the remote backup must be graded with a local backup. You think, what is a local backup? And you can see in the name at the top already, the breaker failure is a typical example of a local backup. And now we've taken the same time grading condition that we had before, but we have included the breaker failure at the top. So let's have a look what happens now. We have the same fault inception. The zone 1 at the top gives the trip command, but there is a breaker failure. The breaker failure is the local backup. It's a local backup, and it will try and now clear this fault locally in that substation. It needs a certain time, because that local backup at the top must also be checked, not that it trips the bus bar, the breaker failure, before the zone 1 had chance to open the breaker. So there's a time grade, typically 120, 140 milliseconds. That's the typical breaker failure time, in which you allow that breaker at the top to clear. If it hasn't cleared after 140 milliseconds, then the breaker failure will issue a breaker fail trip, the so-called T2 time trip, we call it, the breaker fail T2 trip, and that will typically clear the bus bar. Again, you need some circuit breaker time, because now this is going to be the circuit breaker time after the breaker failure trip. And you can see that would then reset around here. So if we then take that time point over here, we don't want our zone 2 to interfere with the remote backup, okay, to trip there, because maybe the fault can be cleared. Maybe there are 2 bus sections at the top, and the breaker failure can clear the bus section. And if we trip, we may trip off the second bus section, which was still in service. So we need to make sure that our zone 2 does not interfere with the breaker failure. So we need to set our time grading step longer than that. And in this case, you can see the 250 milliseconds is still okay, but the safety margin is now significantly smaller, about 55 milliseconds in this calculation technique, but that would be sufficient. So that's the reason why one needs a time grading step. And typically this time grading step is then applied throughout the system. As you go through a next stage that needs to be graded, with that you increment by 1 time grading step as such. And this time grading step is therefore typically defined for a complete interconnected system. All right. At this point, I think we mainly concluded what I'm going to say about distance protection. It's not everything, but I hope enough that I can fit into a small training like that. And I would like to move on to another subject, which is very interesting and closely related to the distance protection, the so-called, or not the power swing blocking, not so-called, but the power swing blocking. The power swing blocking is something where we again look at the system, and we're going to use a model. And the model we're going to use is a so-called 2-machine model. In this case, a lossless 2-machine model, where we have a generation on the one side and a motor or load on the other side. And in between, obviously on the generation side, you have a generation impedance, source impedance. Then you have the XL, the line impedance. So our relay would typically be at the VA, that would be the one bus bar on the left. VB is a bus bar on the right, not the A phase, B phase, sorry. So left-hand bus, right-hand bus, VA, VB. And then the load side impedance, okay, the load impedance on that side. One can typically also consider this to be two sections of a transmission network, the generation side close to the generation and the VM close to the load side of a transmission network. And you can reduce it. A complex network can be reduced to this two-machine model. It's not that we would apply a system with one generator and one motor. The complete power system can be reduced. You can reduce your sources, your generations to one big generation equivalent. And this is very common. If you look at a relay, if you place a relay at the bus A over here, and then that relay with its current voltage measurement will look forward towards the XL, and whatever that relay would see would be defined, a short circuit in front of it would be defined by the source impedance. That source impedance is all the generation behind it. That would be the VG and XG. That's our one equivalent source. You can reduce the entire source of that one relay to one equivalent generation. And the same in front of it, you can have the ZL and the remote bus bar one equivalent load. So the two-machine model is very, very effective in analyzing and modeling the power system. From that equation, you can derive, from that diagram, that model, you can derive this equation here. And I'll show that in a graphic form, but just to show you what we have here is P power. So the power transferred from the generation to the motor, the active power is equal to the VG times VM. So the voltage at the generator side and the voltage at the motor side divided by the sum of those impedances in between it. And because we're using this lossless model, we can have a very simple sign of the angle between them. So let's have a look at the definition of that. That's shown in this diagram over here. What is missing in the diagram is obviously the load current, but that is shown at the top here. You can see the load drops, the three load drops. The load current would effectively be exactly at the bisection angle, vertical at the bottom from the source upwards. That's the load current. Remember, the load current for active power, for P, we get real power is only if the current is in phase with the voltage. Okay, so in this case, it would be exactly in the middle. And the current would flow left to right. There's only one current in this system. There's no other shunts. It's flowing from the generator to the motor. That's the current. And this is the current shown here. And because that current is vertical, in these reactances, it causes a voltage drop, which is 90 degrees. Current is 90 degrees in reactance going to be leading the voltage. That's right. Lagging. The current will be lagging the voltage, sorry. Lagging the voltage, that's why I see, sorry about that. The angle here, it's at 90 degrees to the current that we should not show the vertical current. And that then increases the angle at the bottom. So you can see if the load current were to increase, you can see the angle is going to increase, and if the load current decreases, it would decrease. If the current was zero, there would be no voltage drop, and the generator and the motor would have exactly the same voltage. That is a little bit. And as a power swing indicates, obviously, if the power is increasing, the angle goes up and down between the generator and the motor. And this top diagram, one can show that in a little plane like this, the relationship of that angle, with the angle between the source and the generation here, from 0 to 180 degrees, a simple sine wave. And the magnitude of the sine wave is the P max. The P max would occur at when the sine is equal to 1 at 90 degrees. So at 90 degrees, so when this angle between the source and generation is 90 degrees, we have the maximum current. At that point, no, the current could get larger, but the power does not get larger. Why does the power not get larger? If the angle gets larger, we go, as we'll see on the next diagram, into an area where the voltage starts decreasing very rapidly and then the power gets smaller, because power is current times voltage. So simply increasing the current is not going to just keep increasing the power. At some point, the voltage is going down and then the power will go down again. So that diagram now let's look here and we define some points. The first thing we have to identify is that in a normal steady state operating condition, the PM and the PG are the same, because our problem is the network does not store any energy. Okay, so what power is coming in on the generator side into the electrical system must go out on the motor side. The electrical system, as we have defined it there, has no means to store power. Okay, unfortunately not, I think. So that would be a typical operating point, and we have drawn that here. Then you can see now the current is shown here. I showed vertically in the middle. The current is there in this model, and the generator is over there, the motor is over here, and the voltage drop from the generator side and the line impedance and the motor side is shown like that. The VA would be now our relay location. So at our relay location, we have pure a power factor equal 1. Current and voltage are in phase. Okay, obviously there will be power factors will be different here and there, because there the current and the voltage are not in phase. But here we have exactly power factor 1, current and voltage in phase. It's in our model. 60 degrees, and you can see the 60 degrees is very close to what we call Pmax. Why do we have a Pmax? That Pmax is what is referred to as a theoretical steady state limit. Power, so load angle limit, 90 degrees is that. Why is that so? Because if you imagine that the load and the generation want to transfer more and more power, you can see the angle will shift towards 90 degrees. And when you're at 90 degrees, the current will have increased. Okay, but if you now want to put even 1 watt more power through the system, you will try and increase the current. What will happen? The angle will increase, but you can see the power will go down. And the power that can be transferred, this is an important thing, this is the power that can be transferred. Surely the generator can maybe generate more power, but the electrical system, it cannot transfer that power, so the motor does not receive that power. And then you have a problem, because then there is power, real energy, at the generator side, which does not reach the motor side, because it cannot be transferred. That means the generator needs to store that energy. Generators can store energy a little bit. Sounds interesting. How do they do that? They increase their rotational speed. They store it as rotational energy. The generator will accelerate, and we have then a problem. The frequency will go up, and we get then already a power swing condition. So the theoretical steady state limit is Pmax. Obviously, it is theoretical because we cannot operate there because there's no tolerance. The system will always have some jitter, and if you're sitting at the maximum, the smallest jitter, and you're going to slide down the other side. That's why a practical limit here shown 60 degrees. 60 degrees is a very, very high limit. Typically, you would be operating at Pmaxes around about maybe 40 degrees. 60 degrees is a fairly extreme value already. What is 120 degrees? 120 degrees in this case, if 60 degrees was our operating point prior to a system disturbance, then 120 degrees corresponds to the transient stability limit. Remember, the 90 degrees was a steady state stability limit. 120 degrees would now be referred to as a transient stability limit. Why? This is quite simple. Remember, our generator was generating PG and our motor was consuming PM. And as long as we are on the left-hand side of that 120 degrees, the system can transfer PM and PG. If we go beyond 120 degrees, the system can no longer transfer PM and PG. That means we have passed a transient stability limit. So in a transient method, if something happens, there's a disruption, a fault, then you can move from the 60 degrees, you can move up. But if you move beyond 120 degrees, you've passed the transient stability limit and the system will go out of step. These values are quite interesting for when you apply the out of step protection, which we'll refer to later on a little bit. But for the power swing blocking, it is interesting to know, but it is not of any significance in terms of settings or anything like that. It's just parameters one should know about. Another point you then get to, interesting, is 180 degrees down here. It's so-called out of step point. That's where the systems have turned completely open. It's very interesting in terms of our distance protection. You can see here what happens at our relay A, the voltage is now 0. What will the impedance be? The impedance will also be 0. Remember, impedance is voltage divided by current. No matter what the current is, current will not be zero. You can see the current is really large, the load current. During the point, the load current has increased a lot because we need a big drop between the left and right side, but the power transferred is zero at the relay location because power is I times V times cosine phi, and cosine of 90 is zero. There's no real power being transferred, only reactive power, VARs. No watts, only VARs at the relay. But the impedance is zero, which is a problem. Okay, these diagrams are very interesting, but remember we are looking at the distance protection, and the distance protection we're used to seeing impedances. These are voltages, okay, remember it's real voltage. Okay, current was also shown, but the voltage, these I times Z are also voltages. We are looking, and to transfer these voltages into the impedance plane, you simply divide all the IX voltage drops here by the current, and then you get reactance. Okay, so try and take this diagram that we have here now, and I'm going to transfer it over here into the impedance plane. Now we have the impedance plane R and X, and we draw a circle because the trajectory of the power swing as we move from that 0 degrees, you see right at the top 0 degrees, to later on we'll see the 180 degrees will be at the origin. That trajectory you move on in the impedance plane is a circle. It's a bit, just for clarity here, obviously in a theoretical point of view, was that lossless model. Remember we had a lossless model which was just X, and at 0 degrees the current was equal to 0, so the impedance would be infinite. Okay, now I can't draw infinite in a circle or any plane, it's somewhere off the range. So that theoretical case we actually had there would be the special case of a circle where the circle has an infinite radius, a straight line. Okay, and that point 0 would be infinity somewhere on the left or right hand side, depending on which, if we're on the generator or motor side. But in the practical sense, we will not have a perfect lossless system, so the power swing or the trajectory will be a circle. And the position of the circle, interesting enough, also depends on whether the voltage on the generator side is a little bit bigger physically than on the motor side. That can also be, the circle can be below or on top, but at the end of the day, it'll be a circular characteristic, the trajectory of the impedance during a power swing. So let's look at some points. 0 degrees will be far outside, and the measurement will be not really possible because it's at current effectively 0. We're not measuring any effective current, so an impedance measurement there is very theoretical. But once we leave the point 0, we get to a very real impedance we can then measure because the current then is no longer 0. So this is unfortunately a little bit of a theoretical point, this angle 0. Also, when you see it later on doing tests, will not be practical. And you can see the big distance between a theoretical point 0 and 60 degrees. It's very interesting. If you see a circle, typically, if you're going to divide a circle up into angles, you think 0 degrees, somewhere here 90 degrees, 180 degrees, and so on. Not the power swing circle. The power swing circle, unfortunately, 0 degrees, and you can see the 60 degrees is down here. It's what we understand. If you think of a distance relay, the distance relay is sitting there at the origin of this diagram. And what would you have under a typical load? If you have a typical load export, you see the load somewhere here. Okay, maybe depending on the power factor in that range. You see it in the RX range somewhere here. That's where you would see your load impedance. So this is really quite understandable for us now. A normal load condition, or not normal, very high load condition already. Remember I said 40 degrees would be normal load. 60 is a very, very high load condition. Would probably not, if we set our relay correctly, will be either in the load cutout, but not in the reach of our distance setting. So our distance setting should not encroach into that. That's what we apply. We apply load encroachment, other factors to prevent the distance relay from seeing this inside its characteristic. Remember the next point was the 90 degrees, not so interesting, but the 120, our transient stability limit. So a power swing, in theory, if there was a disruption in the system, the impedance could move from that 60 all the way up to 120, and now you can see that could be inside. So between that 60 and 120, we could be inside the distance relay reach, and we don't want the distance relay tripping because it's not a fault, it's a power swing condition, and we need to apply the power swing blocking for that. Okay, and obviously if the swing continues to 180 degrees, in theory it could be at 0 ohms, okay? This circle does not have to go through the origin. Okay, just to mention, in this case, it goes through the origin because our relay that's measuring this is sitting at the so-called electrical center. So it's sitting exactly halfway between the generator and the motor. If we are sitting a little bit to the left or right of that point, the circle will cross either above or below. So it'll be a circle crossing not exactly, but that doesn't matter. The trajectory will come into the impedance settings here, not necessarily going exactly through the origin, but this is one example, just to understand. All right, for this setting, now we're going to come to the passing blocking settings in the relay. It says there are no settings required. Obviously, you need to set what you want to block, but you don't have any settings that you have to set the frequency or the blinders, or there's no complicated settings needed because the passing blocking function works autonomously. It's very effective, can detect swing frequencies of up to 10 hertz. So it means that you have 10 rotations per second, which is normal power swings will be in the range of about 2 hertz, up to 2 hertz in a normal power system. But if you leave it there, eventually it can accelerate up to that speed, but that would be very, very unusual. So the maximum power swing frequency is not an issue. You can detect the power swing during single pole open conditions. We'll show that in the diagram later on. Okay. If the power swing changes to a fault, it'll unblock. We'll look at these conditions later on. So this is just some features of the power swing blocking. Out-of-step protection in CPROTEC 5 is a separate function, okay, that you would use. If you want to use out protection, it's the same principle behind it, but it's a different thing. It's not distance protection. It's a function that you apply to recover, like say disaster, one can call it. If the system has a real serious disaster in a system where it's like cascading tripping, then you need to island the system. It's a separate concept, not a distance protection concept, and therefore it's a separate function, out-of-step protection function in the CPROTEC 5 relays. So how does it work in principle? Just quickly, we need to move a little bit. The power swing detection will apply around your set zones. You see the yellow would be your distance set zones, your largest set zone. Automatically, no settings required. It'll automatically in the background apply a boundary around that, and then it'll monitor the impedance on a continuous basis. And each of these red dots is measured impedance is separated by about 5 milliseconds. So you can see it does a measurement, then every 5 milliseconds another one, and measures the impedance and then checks the trajectory continuously of that. And that's done all the time, even if the impedance is far outside the pickup characteristic. All right, that block, then you can see there as it moves into the characteristic now, it needs to, if it moves there, then your distance relay would start picking up and trip, and so we have to have the blocking active by the time it reaches the set zones. And the techniques for the blocking use a lot of criteria, and only a few have been extracted here for the explanation. I don't want to go into all of that. It is really, really very intricate function in terms of the detection. But to summarize quickly, we have here a monotony criteria. That means it must keep moving in a defined direction. You can see here we have the delta x's decreasing and the delta r decreasing. You can have a change of the x, but the r was still decreasing. This would still be a power swing. This is a fairly monotonous movement because only the x change direction, not x and r. That would be a normal smooth trajectory, as one would refer to that. On the other hand, if you get an abrupt reversal like that, that is not what a power swing would do. A power swing would not do an abrupt reversal like that. That would be a criteria to reset the power swing blocking as one of the criteria, not the criteria. It's a number of criteria working in parallel. The continuity criteria is rather interesting, because if you have a power swing, obviously you can have a stationary load somewhere, but that's not inside the relay where it enters the relay. Once you have a power swing and the thing starts moving, it has to keep moving. If it should all of a sudden decide to stop like this, then it is no longer a power swing. Because remember, if it's inside the relay characteristic, this is somewhere at 120 or 150 degrees on our circle, remember, that is not a point where the impedance can stop. It can stop at 60 degrees or 40 degrees, that's somewhere out here, but not in there. It cannot stop. If it stops there, it's a fault, typically a three-phase fault. Very, very unlikely to happen, but some people like to test things like that, and the relay will detect that and reset the path swing blocking if that happens. The smoothness criteria is a very commonly one that's used to check, because that's also a very interesting one. The distance between each of these measurements, remember, every 5 milliseconds you measure impedance, the distance is going to be fairly constant because the rate of movement is quite constant. And it's also interesting, I didn't mention that earlier. If you remember that circle we had before with the 0 degrees at the top, 180 at the bottom, the movement when you're close to 0 is fast. When you come to the bottom, the movement slows down. Okay, so where it is interesting for the relay, the power swing impedance trajectory movement is fairly constant, fairly slow, but it must be continuous. It cannot jump. It cannot be slow and then have all of a sudden a rapid jump like that. That is not possible. That would be a reset. The jump of the trajectory would be a reset criteria for power swing blocking. This is just an interesting diagram just to show. Remember, we had a circle all the time some years ago. Some student in the development department made a model with 3 machines, not 2 machines. And you can see if you have 3 machines swinging, they can swing at different, they interfere with each other. So 3 machines interfering, and then you get a slightly, but you see the movement here is smooth. There is no jump in there. It is like moving along a fairly complex path as such, the 3 machines swinging, but there are no jumps. This is just a continuous power swing. No fault or anything, it's just a power swing. And the advantage is obviously the other older or historic way of measuring power swings was using blinders. And it was just to show that with the blinder technique, it's difficult. But the blinder technique sees when you cross the one blinder and it starts a timer, how long till you reach the other blinder. And you can see there will be some difficulty here, because you sometimes cross the one and you don't even reach the other one, go back out. And so the blinder technique will not work, whereas the power swing detection as we have implemented in CPROTEC 5 works quite well. It's the same power swing detection as it was also used in CPROTEC 4. Now some diagrams just for interest. This is a power swing, and you can see the power swing blocking at the bottom is picked up. Unfortunately, I must apologize. This is done with CPROTEC 4, but as I said, the technique is still the same. It's around about a 2 hertz swing oscillation we see here, and you can see the typical characteristic of a swing. As the current increases, the voltage down here decreases, and you can see around the left there, the power swing is there, and at the bottom of power swing detection is picking up and blocking. And then over there, you get also the pickup by the relay as it swings in. You can see where the current reaches its peak, the voltages go down, the relay actually picks up, but no trip because the power swing blocking prevented the tripping. Then over here, in the middle of the power swing, you get a fault condition. You can see the fault is here on the C phase. The C phase current is now a fault current. The fault current magnitude is smaller than the power swing current. Over here, the voltage just stops. Obviously, the voltage does not continue with its trajectory, stops. And you can see the pickup of the C phase zone 1. Okay. In this model, the tripping was not done to the break. Otherwise, the current would have stopped. It would have a single pole dead time here, but it was just, unfortunately, the model used at that time did not really trip the breaker. It was to show the zone 1 trip would have come, and the other phases, the power swing blocking stays on over here. That is clear. It's one example. That's another example here. Here, the relay now does trip in the A phase, and you can see the dead time. You get the power swing continues in the remaining 2 phases. And here, it's a more accurate simulation. You can see the power swing frequency is not constant. It starts off with, you see the swing frequency, you can calculate from the dip here to the dip over there, and the next dip over here. The time interval there, that's one rotation. That's from basically here, 0 degrees back to 0 degrees. That's one times around the circle. And you take the time difference there. I can't read that exactly now. That would be related to the frequency. I think it's around from 2.5 seconds to just under 3 seconds. So it's just under half a second. So it's around about going to be a 2 to 3 hertz swing. But you see, as we move on, the interval gets shorter and shorter. The swing frequency is increasing. So at that point, we have around about a 2.5 hertz swing. And then right at the back, we have an interval of about only 250 milliseconds, around about 4 hertz at the end. So the swing frequency changed there. But it doesn't matter. At the bottom, you can see the power swing in the open pole is obviously reset, but in the two connected poles B and C, the power swing blocking is active and prevents tripping during the one pole dead time. That's the fault inception. The power swing blocking resets. And that's the reclosure. And see, after the reclosure, the power swing continues and the power swing blocking becomes active again, and there's no tripping of the relay due to the power swing blocking. That's just a note. Okay, in CPREC 5, you will not see that gap that is shown here. In CPREC 4, you did see this. So if you see this gap here, that is not relevant. The power swing blocking is still active there, and that's why in CPREC 5, you will not see a gap there. But in CPREC 4, there was a 80 millisecond timer, which when the measurement drops, what you see is the measurement drops off due to the jump, but there's a delay on reset of the function of 80 milliseconds, which bridges that drop off there in CPREC 4. In CPREC 5, we changed the signal output. The signal output includes the stability timer, so you don't see the gap on CPREC 5. The functionality is the same, but you are still blocking in that gap, but you get some more consistent information you see in CPREC 5. And one of the final things I want to show here on the power swing blocking is an example. Here you have a transmission system with 2 feeders and 4 relays, D1 to D4 on the transmission system at the top. And at the bottom, you have here, this was in some South American country, I don't remember say which one, but it's I think it was 220 or 300 kV, long transmission lines, and this was a bus bar pretty much in the middle of the transmission system. This is the load side and somewhere quite remote generation there. And what happened on this bus bar, somewhere in the middle of this transmission system, there was a distribution transformer, and on the LV side of the distribution transformer was a fault, and that fault was not cleared immediately. I think it was some animal on the LV side of the transformer, and it was somehow not cleared properly or it stayed on for a certain time. So try to visualize this, and we will look at one of these relays. I can't remember which one of the 4 relays here, how it would see this fault on the LV side of the transformer. So the 3-phase fault over there, let's say on the LV side of the transformer. And what you don't want is a trip of any of those feeders. That would be a disaster if your transmission system trips due to a fault on the LV side of a transformer connected to the one bus bar. And here you can see this is the D4 relay. Okay, we can maybe go back. See, D4 was the relay over here. This relay sees obviously that fault in reverse direction. Is what you will see now. You see there's a load condition transferred. So D4 is actually not quite, the load would have been on the other side. Sorry about that. I think the diagram not that accurate. So remember, so far as I remember, the load did come in from the left-hand side, right-hand side, but just a symbolic diagram, this one. Then you jump to the reverse fault. Okay, and then this reverse fault stays on, and now the voltage on that bus bar, that transformer connected bus bar is dropping. And remember what happens if voltage drops, the transmission system can no longer transfer the power, and the angle is going to increase. We're going to go into a power swing condition. So we jump onto a circle. There's our power swing circle, and that's going to circle right into the zone 1. And that means we would trip the transmission system. So the power swing blocking needs to pick up at the bottom before we reach the zone 1 and then block it. And that's what happened correctly, and there was no tripping, no incorrect tripping due to that power swing. Take the power swing and no trip when you swing through the zone 1. All right, I think because of the timing constraint, I want to jump to the question and answer, because the rest of the power swing here is not really that interesting, and we still need some time for the auto recloser as such. So I want to, I think, jump to the question and answers at this point. Thank you.
Yeah, thank you, Gustav, for this interesting second part. And time is really running. So I will only have one question for you. I hope I picked a good one. And this is the question from MT. Do you have an example for underground cables, since tower footing and arc resistance may not be applicable? Am I right? Of course, this would need another half an hour, I guess. Maybe you can.
If you have underground cables, obviously you do get an arc in the dielectric of the cable, but that you need to calculate that in a different manner, because it's not the same as the arc in air. And typically you would use rule of thumb, a certain arc depending on dielectric, but that one has to discuss separately. there's not that many parameters or information on that. For medium voltage, I have some data, but for transmission cables, I don't have data then.
Okay, and then maybe one more question that you can include in your third part, because it is about auto reclosure. How is the importance, or how important is the auto recloser usage to sustain the grid power without breakdown?
Well, the auto recloser, obviously, as the name says, it's part of the protection and it automatically recloses. So it basically reduces the impact of the tripping due to a fault. And on transmission lines, you get, I think, I don't know if we have the numbers later on, around about, it depends on the environment, maybe 5 to 8 or 10 faults per 100 kilometers per year. It's a lot of faults. And if each one of those were to just trip and leave the brake open, it would affect the system availability, and the availability would then obviously affect the quality. So therefore, auto recloser is very, very effective on overhead lines because it reduces the impact of most, and 80% of those faults, as I say, are transient. So the auto recloser is very, very effective for overhead lines.
Okay, and I hope this keeps you curious about our third part as introduction. And now we have another small bio break, about 5 minutes, because the content is tough, I think, and it's hard to concentrate over 2 hours. So see you in 5.
Okay, till later.
So welcome back from the break. We are a little bit behind the time. We will extend the session a little bit, but if you have to leave on time, just simply watch the recording afterwards. Now final sprint, I would say. The topic of the last part are auto reclosure with secondary arc detection and measured voltage failure detection.
All right. Welcome back. Thank you for being so patient. Let's get into this interesting subject. It's auto reclose, but I'm going to focus very much on the secondary arc detection, which is a very, very interesting feature we have. The auto reclose in general, trying to keep it brief, is done in the following manner: that you have a short circuit, all right, which will have a fairly large primary fault current, and then depending on your application, you have then a 1-pole trip or 3-pole trip. This is done by the protection, and the auto recloser is always started by a protection trip. This is just the definition of that. Then two things can happen after the trip, okay, either 1-pole trip or 3-pole trip, it doesn't matter. It is either a permanent fault or an arc fault, okay. If we're on the 3-pole tripping side, then the secondary arc detection does not apply. The secondary arc detection only applies to the single-pole tripping. But remember, single-pole faults are approximately 80% of the faults on an overhead line are single-phase faults. So the single-pole auto reclosure is a very effective means to get good system availability. So if we stick to the single-pole tripping side, then you see the two conditions, the permanent fault and the arc fault. If it's a permanent fault, then at the bottom what would happen, the auto recloser would come and it would not be successful. So you would reclose after the 1-pole dead time, and you'd have to then trip 3-pole, and it will be not successful. If it was an arc fault, basically a transient fault, then that arc would typically extinguish during the dead time if the dead time is sufficiently long and the coupling and the system conditions allow for that, and you reclose after the extinguished arc, then you have a successful auto reclosure. If obviously the arc is not extinguished, again you would have a non-successful auto reclosure. Those are the conditions. Now, that is just classic auto reclosure. How can the secondary arc detection improve on that? And we'll have a look at that later on. So first of all, the advantage, I think we had the question earlier. Yes, auto reclosure is a big advantage for system availability, and the 1-pole even better, because during a 1-pole dead time, you don't have lost synchronous power flowing, so system stability is much improved. That power swing stuff we spoke about earlier is not going to be that apparent. If you have a 1-pole trip, the risk of a power swing is much less than if you have a 3-pole trip after a fault. Technical challenges for the 1-pole auto reclose is obviously you need to set a dead time that's sufficient for the secondary arc. Now we'll expand the secondary arc just now to disappear. And the probability of an unsuccessful 1-pole auto reclose is if the set dead time is too short, because then the arc has not got enough time to extinguish. If it's very long, then you have an unnecessarily long dead time. But there are a technique to improve on that. And that technique is the secondary arc detection. But before we get there, let's just briefly look at the 3 stages of a typical single-pole auto recloser. The first stage is the fault. Over there, as I said, fault current, a large fault current, protection relay is operating, gives a trip command. The trip command will be then followed by the breaker opening. So we go into from the auto reclose point of view into the second state is when the breaker is open. Now we have the 1-pole dead time. And I'm going to assume that the remote side has done the same thing. I'm not going to worry about any inconsistencies. So both sides have a 1-pole dead time. Then you are in this middle condition. And this is very interesting because now you can see I draw the capacitances in here. The healthy phases, the top 2 in this case, will couple via capacitance to the open pole, that both sides are open, and there will be a continued current flow via the arcs. Remember, the arc was there from the fault condition at the beginning, ionizing the air. Remember that 2.5 kilovolt per meter and the large fault current, and a lot of, you've seen some videos of this, like really magnificent arcs. That does not go away very quickly. We are talking here sub 1 second, and that's a fairly short time for this gas to get blown by the wind. It's a typical 1-pole dead time, around about 1 second. That would be this middle condition. The arc is still there, fed by the capacitance from the healthy phases, the secondary arc condition in the middle. If things go well, after a few hundred milliseconds, up to maybe a second or so, that arc will then disappear, and we then go to the final state. You can see the switched off line is here. It's still coupled with the capacitance. There will be some voltage on here due to the capacitance, but the arc is not, has gone away. And we can, by monitoring the voltage over here, you can see this arrow shows you the voltage there. Because remember, our relay is sitting here. If we have line side voltage transformers, we can monitor the voltage here on this switched off line section. And we can see this condition, the secondary arc, using that voltage, or here see that the secondary arc has disappeared. And we can use that for a very effective way of controlling the auto reclose. Motivation. Why do we want to use the secondary arc detection? All right. We want to use it because the fixed dead time can be unnecessarily long. Here we have an example. See right on the left there is the pre-fault condition for about a cycle or so. Then you go into the fault condition there for about 3 or 4 cycles. And then you can see the trip. But the voltage, and this is the voltage on the faulted feeder, does not go to 0. Okay, because it's coupled. Initially, we have the secondary arc only for a very, very short time. In the second dotted line, you can see there the secondary arc has already reset. In theory, we could have reclosed all the way much, much earlier. But typical, you hate here, it's about over, it's about a 1.2 second single pole dead time. You wait and wait and wait, and only reclose with a much, much unnecessarily long dead time. This is very common. Another problem can be obviously a metallic fault. And you can see here the same condition, pre-fault condition, then the same first dotted line is the protection as tripped. Then the first dotted line is the fault inception, the second line, the relay trips, and you can see the voltage is 0. There's a metallic fault. It's a single pole trip, and the voltage will not be 0 unless it's clamped down via a permanent fault. It's a permanent fault. The auto recloser does not know this and will reclose here unnecessarily and cause a switch on to fault, and you have to trip again. System stress, very bad for power system stability and so on. Unnecessary, this recloser here. Secondary arc detection can prevent that. We'll see that later on. And the third one, maybe not that common. What happened on the third case over here, again a fault, but in this case, maybe it's a very long line or whatever. The secondary arc did not disappear. You can see this funny waveform here. It's got a lot of harmonics and spikes and so on, and that is the characteristic waveform of the voltage during a secondary arc. It stays on. That means the arc is not gone. So when we reclose after the dead time, the arc is still there, the fault is still there, and there will be a switch on to fault, and you have to trip again. The difference between this one and this one is here, it's a permanent fault, probably a physical damage, a conductor touching the tower or something like that, metallic fault. There, no recloser makes any sense. Here, it's interesting. You have a secondary arc. It is an arc fault. If you had changed here to a 3-pole trip, then the 3-pole auto reclose would have most likely have been successful. Because remember, during the 3-pole, there's no more capacitive coupling into the switched off feeder. There's no secondary arc on a 3-pole fault. Those are the 3 conditions. So now, if you're going to apply the secondary arc detection for the auto recloser, it will improve the performance there significantly. Okay, we'll have shorter dead times, no reclosure on permanent faults, no reclosure on metallic faults, and so on. That is obviously a big advantage. In order to implement that, as I said 3 or 4 slides back, we need the voltage on the line side. So it must be a line side connected VT, and basically in the Dixie 5 routing, you route here on the circuit breaker. This voltage transformer is typically for operational measured values. But in this case, this voltage that you have routed here will also be used as your voltage to monitor the secondary arc. Okay. I think the text slide one can jump over. From a time point of view, it is not that interesting. I think I've said everything that is to be said there. You can apply this together with a classic auto recloser. The secondary arc detection will be the first cycle that you use, and you can apply additional auto reclose cycles, but they will always be the second, third coming after the secondary arc detection if you apply that. This logic diagram just shows you on the right here, the output signals, which we'll look at in a little bit of detail later on. You are monitoring the voltage on the basically switched off feeder, and if it is too small, then it will be a metallic fault, basically no reclosure. You will always see a voltage, especially after the secondary arc is extinguished, the coupled voltage over there. And the little block on the complete left there is a logical block, a multi-criteria block. We don't use a single criteria, we use multiple criteria to detect the secondary arc presence and also then the secondary arc extinction. And if after the minimum dead time has expired over here, the arc has disappeared, then you'll basically allow the reclosure because the secondary arc has disappeared. While the secondary arc is there, you give the output, I'm detecting one. And basically, if it does not disappear, then obviously you go to the top and say, cannot reclose because the secondary arc did not switch off. So we get all the information we need to practically implement this. In Dixie, it's quite simple. You go into your library, and your system library, you find there under the auto reclose the secondary arc, and you insert that into your circuit breaker where you typically would have your auto reclose function. And if you want additional cycles, you would place them at the end. So in the settings, you can see the secondary arc detection auto reclose settings are exactly the same as the normal auto reclosure. The only difference is the cycle, the secondary arc cycle has got two additional parameters, which we'll look at in detail later on. It's your minimum dead time and obviously a maximum dead time. There is no fixed dead time for a secondary arc. The secondary arc only has a minimum time and a maximum time. If after the minimum time, the secondary arc has disappeared, it'll reclose immediately. The secondary arc disappears very quickly, can go even quicker, but we will have some graphic examples. I'll show you those two timers in graphs just now. It's more clearly than on the text slide. That's the text definition you see there. The minimum, those two parameters, the minimum time, this is the minimum dead time after a one-pole trip. Closure will not be done before this time has expired. And the maximum dead time, as the name says, this is the maximum time if the secondary arc or whatever is still present at the end of the maximum time, then the cycle is aborted, okay? And you have a three-pole trip and nothing after that. Some graphs, it's always more interesting than a picture. Here you can see a nice large diagram of the voltage, only the voltage now. And you can see starting on the left, pre-fault condition, then the drop of the voltage under the fault condition, then the breaker open and the secondary arc up to this dotted line is secondary arc. And you can see the transition here from the secondary arc to this one. And there you can see it's a nice 50 hertz or fundamental frequency signal. It has got some transient in it here. This is due to other influences, but it is a clean signal. No, hardly any harmonics or anything. It's coupled from the healthy phases. Over here, it's a burning arc. Okay, that's why you see the significant harmonic and other factors we can detect. And we detect the secondary arc. You can see the alarm up, secondary arc detected. When the secondary arc disappears, you can, in theory, permit closure immediately. There is a stability time, a so-called restrike timer, just to put it. Could be that it disappears and then it restrikes here, then you don't want to release the close. So you have a monitoring time, 150 millisecond restrike monitoring time. After that, the closure is then released. You can have a much shorter dead time in this technique. All right. Alarms, if you're going to apply this, then it's very interesting to look at the output signal. I call them alarms, the output signaling of the secondary arc detection. You have here the three. Secondary arc is detected, no closure because the secondary arc did not go away. That would be the arc doesn't extinguish because the very long line or other influences, or metallic fault. These are the reasons for no closure. Either secondary arc did not go away or metallic fault. Metallic fault, you lock out the auto reclosure. Secondary arc didn't go off. Maybe you do a three-pole trip and a three-pole auto reclosure. That's optional, what one can do as a response to that happening. Right, and just to summarize that quickly, finally, we look at the three cases that we have. Case number one, this is a secondary arc detected. And you can see here, secondary arc extinguishes around about there, and you can see that in the alarm. Sorry, I think it's German, but it doesn't matter. The secondary arc detection drops off over here, and then it permits the closure here because the minimum dead time has expired. It gives the close command. The second case over here, no reclosure. Why? Because the secondary arc doesn't go away. You can see the secondary arc condition stays. and all the way over here, the maximum dead time expires, and then no reclosure because of the maximum dead time expiry. Here, similar situation, fault, trip, but now the voltage is very small. It's a metallic fault again, no reclosure because metallic fault was detected. Works effectively like that. The internal timers, as I said, I'll have some diagrams explaining them. We have the two timers. There's the restrike monitoring. That is a fixed timer. It's internal, 100 milliseconds, no setting required. And you have the effect here that you see a very, very short secondary arc. This is a German customer we have. He's got a strange configuration where that can happen, where you can see the fault. When the fault is cleared, there's almost no secondary arc. It's half a cycle of secondary arc, and then you have the minimum dead time needs to expire. So you don't want to then release the close basically after 50 or 70 milliseconds. You need to wait the minimum dead time. That's why we have a minimum dead time, because it could be that the secondary arc is there for an extremely short time only, and you don't want to stress the breaker by reclosing within 20 or 50 milliseconds. So typically around about 150 millisecond minimum closure time. The second example, you can see here, the arc was on a little bit longer, but still the minimum closure time has not expired. So you have to, when the secondary arc extinguished, you have to still check the restrike monitoring time, and still it's too short. The closure is only given after the minimum closure dead time at that example. Here the arc is on a little bit longer. So you can see the secondary arc extinguishes, the restrike time. Now the minimum time has expired, and we can close immediately after the restrike timer. Metallic faults are a problem and blocked. Okay. I think that concludes the secondary arc detection for this presentation. If you are interested, there are some application notes and the manual explains it in detail. The final subject, very quickly, that I want to look at, but is also related to the distance protection, is the measured voltage failure detection. Just in a couple of slides to look at that quickly. The measured voltage failure detection in CPREC 5 has got three aspects or three sub-functions shown there, 1, 2, 3 with the arrows. You have the one for the unbalanced faults, the classic fuse failure monitoring detection, as it was done in relays 2 generations back. That was the only one had. Then in CPREC 4, we introduced, in addition to the unbalanced one over here, the three-phase measured voltage failure detection, or three-phase fuse failure, if you want to call it that. That is a more intricate function. And the final one at the bottom is a fairly specific, that's switch onto a measured voltage failure detection. That would be the condition where, for example, the voltage MCB, the switch is switched off and you energize the line without any voltage. And typically, if you get under impedance protection, under impedance starting, Z smaller starting, you have some load current, the distance relay will trip immediately. But if you have some overcurrent or other starting techniques and the distance relay does not trip immediately when you energize the line without voltage, then you would get no indication. So, but this function would, with a small time delay, indicate that there is a energization without voltage. So three functions. They have got in the settings, you can see them, they can be applied here. You have some setting parameters that apply to the stages, and the one at the bottom you can switch on and off. This final one is the only one you can, when the entire function is switched on, the 1 and 2 are always active. The 3 you can individually turn on and off with an individual setting at the bottom. All right, the logic diagrams, screenshots from the manual. So I'm just going to briefly explain what is relevant here. The asymmetrical or the standard fuse failure technique is monitoring this negative sequence voltage, that U2 is a negative sequence voltage and U1 is a positive sequence voltage, and there are no settings required, okay? It is a simple ratio. It's a fixed ratio. When the negative sequence is bigger than 40%, when we check this, and this works under all normal fuse failure conditions, it'll pick up. So if you have a negative sequence voltage, then the fuse failure protection will want to pick up. Obviously, you can get negative sequence voltage during fault conditions, but in a power system, you cannot get negative sequence voltage without negative sequence current. So you can always see in the classic fuse failure or measured voltage failure detection, is always the voltage is the pickup criteria and the current is the blocking criteria. So you can see the presence of negative sequence current further down, I2, will go in and be the blocking input. So you can see the current inputs come through the bottom, and at that AND gate at the top there, all over there, it's a negated input at the bottom. It's where the current comes in and will block the fuse failure detection. Again, the only setting that you need to require is the current setting. And if you have ever done this, you apply the current threshold at the bottom. If the current threshold is coordinated with the distance pickup. So when the distance relay minimum phase current for pickup should be effectively larger, not smaller than the fuse failure, because the fuse failure must always be able to pick up at the same time similar sensitivity or higher sensitivity than distance protection. So it will be able to securely block. Okay. The other setting at the bottom, which I need to mention, unfortunately, the dropout failure is also not that clear, the application, because if you now go into a fuse failure condition, then you see some time delays over here. Initially, it is a blocking, very, very fast blocking, but it could evolve into a fault. Remember, the fuse failure, maybe it is really a VT failure, but it's the primary fault on the VT and it turned into a real short circuit. Then you want to unblock and trip. So initially, it's not latched. Later on, you see there's a flip-flop. It is latched, but that's only after 10 seconds typically. If the fuse failure is there for 10 seconds, you say, okay, right now, this is probably in the secondary wiring some problem, and I need to latch this. Why do I need to latch it? Because it will take some hours or some time for the operator to get there to fix the problem. And in that time, the fuse failure blocking must remain on. And if you now get an external fault or some fault in the system, creating negative sequence current, you cannot have it immediately resetting the fuse failure. And that's where the setting at the bottom comes in. Some users want to do this. I say, even if the fuse failure is active and has been active for 3 hours, if there's a negative sequence current, I want to immediately reset. In that case, you must set that parameter at the bottom there. Asymmetrical fail dropout on network fault, and you say set it to yes. And then this will, as soon as there's negative sequence current, will always reset the fuse failure. Not what I would recommend. The recommended setting is no, but that is something one must do for the application person to check. The other fuse failures I want to just do very briefly due to time. Maybe you can check the logic in the manual yourself. The three-phase failure is a delta technique. Basically, it will see a change in voltage, and it's important the voltage must change to a very small value. You have thresholds that you can set. Don't set it too sensitive. I think classically there were levels secondary voltage of 5 volt, I think set. Recommended would be a voltage of at least 15 or 20% would be a good minimum phase voltage. So because it cannot come during any weak in-feed or under conditions, because if there's any delta in the current and extremely sensitive, it will not be a fuse failure. The three-phase fuse failure can only happen if all 3 voltages jump to 0 and there is no delta in the current. That means that it is simply a secondary VT circuit failure, 3-phase. Typically, if you switch off the VT with the MCB. That's that one. And then the last one, as I said, the switch on one is the unusual one, is time delayed. So you may see this sometimes if you have a relay and you simulate the circuit breaker auxiliary contacts to be closed and there's no voltage connected. You can see the one pole open or that one pole closed condition will be true. Greater than one pole closed, typically 3 pole closed is true, and you have no voltage. Okay, so at the bottom you see no voltage and 3 pole closed. This will pick up. It doesn't matter. It just means that during this breaker closed, simulated closed condition with no voltage connected, the relay would indicate there's a failure. As soon as the voltage comes, you can see it's without any delay. As soon as there's a voltage present, it will reset this, the bottom input. So this is a, but if you were to energize the line without voltage, then after the set time delay, this fuse failure would pick up and tell you, look, the line has been energized, but there's no voltage. All right. That concludes that really just with the final information of what the VT does. Obviously, the VT will detect failures of the VT circuit, basically broken conductors. It'll block the distance protection, block the directional negative sequence protection. Those are protection functions which could operate without or very short or no time delay and would be non-selective without voltage. And also the ground fault, high resistance ground fault uses direction measurement. If the VT fails, obviously it has no direction, those directional stages would be blocked. Optional settings, you can set it to also block other functions like normal directional overcurrent assist, over voltage protection or under voltage can all be optionally set to be blocked. Okay. Questions or answers or questions and answers?
I have the questions, you hopefully have the answers.
Hopefully.
Yeah, I think we take the time for like 3 or 5 more questions. The most questions are about the first 2 parts, about the distance protection. And I want to start with a question from EA. What is the effect of transposing of parallel lines on the measured fault location?
Right. This is common that longer transmission lines are transposed, and the transposition means that you take the outside conductor to the middle and the middle to outside, so over the entire line length is balanced. Remember I said the impedance we use in our calculation is the positive sequence impedance, and I said it would be if it's symmetrical, that funny diagram we had. Now, if you don't transpose a line, it will not be symmetrical, okay? And the effect of a non-transposed line can be as much as about 5 to 8% impedance difference between a loop. Basically, an A to B loop would be an outside loop to a middle loop, or an outside loop to an outside loop. So the impedance A to C, if these are the 2 outside loops, could be about maybe 5 to 8% bigger than a loop A to C if A and C, one of them is a middle loop. This would be for a vertical construction. It depends on the tower construction. So it is a difficult question. It can have an impact, and obviously you need to consider this, but the transposition helps. If you have a transposed line, it improves the symmetry. So non-transposed would be the problem, not transposed. So non-transposed, you may have to set your reaches a little bit, not 20%, but 25% over under reach to make allowance for the non-symmetry of a non-transposed line. Transposed lines are good, non-transposed lines are a problem.
Okay, thank you. Now, next question is from FH. Is there a dummy software relay program which we can test and learn without connecting to the system? Maybe I take this real quick because I think we can take this question to promote our CPROTEC 5 digital twin solution. Yeah. There you can simulate all our CPROTEC 5 protection devices, inject some currents, some voltages, or even replay a COMTRADE file. Yeah, this would be exactly the solution for you, I guess. Okay, back to the more technical questions. Yeah, maybe a more complicated one to challenge you a little bit. The one from WS. The arc resistance calculated for distribution will be relatively small due to smaller towers. What are the consequences of setting the resistive reach to a larger value than calculated by the arc resistance equation specified?
Yeah, that's an excellent question, I think, because there was not that much time. But the symmetry, when I showed the symmetry diagram, then I said that I had, in that case, a ratio of 0.5, and I said increase it to 1 to get it to an equal value. The only risk, and I think this is not going to be a problem in distribution, is that your very large resistance setting goes into a load encroachment. And I think in distribution, that is not going to happen. So setting a larger resistance is not going to be a problem, as long as increasing it to meet the symmetry factor is never going to be a problem. As I say, but you should, if you have that situation where you've got a very small resistance setting and you need to increase it or want to increase it due to symmetry, as long as you go to a factor of R being 1-to-1 with the X, so basically 1-to-1 ratio, or even a 2-to-1, or maybe 3-to-1. If you go beyond 3-to-1, you should not really unnecessarily increase the R beyond 2-to-1. Okay, if you're happy with the R setting that's small for the arc requirement, but for symmetry you want to increase it, If you go up to a ratio of 2 to 1, so R twice X, that's fine. There's no problem. There's no negative impact by that.
Okay, no challenge for you, I see. So maybe take one shorter one from MOD. Does fault right through affect the time setting for zones?
But fault right through, I assume the fault right through is something to do with renewables. I don't understand, was the setting for the time setting for zones is a grading of distance relays to each other. The fault right through term to me only makes sense in terms of renewables, and that would be meaning what the renewable generator does under a fault condition. Now, if that could be that you have a T along a line and the generator or windmill feeding on as a T onto a line is set to fault right through, then obviously that is going to affect your auto reclosure decision, because you would not want to do an auto reclosure onto the generator still to connect it to a faulted line. And fault right through should then in that case not be set on. It should be to separate during a fault. So the method of doing the renewables is a different subject. But other than that, I cannot relate fault right through to a zone time setting.
If you need to get deeper into this topic, or maybe you misunderstood it a little bit, you just simply get in contact with us. Okay, I think due to the time, enough questions for today. The most important points once again: all the questions that are still open will be answered later in a written format. Yes, you will get access to the recording and to the slides. For this session, we won't provide a certificate or something like that. If you are interested in a more extensive training, receiving a certificate, or even some hands-on sessions, you can book always a training at our Power Academy about also, of course, line protection. And we also will continue our line protection series and plan a session or two about differential protection, or line differential protection, maybe in summer or autumn. So yeah, please stay tuned, stay in contact. And thank you for all your questions and your participation. Thank you, Gustav, of course.
Thank you, Nina.
And have a good day.
Have a nice day.